Right. I take it everyone can see that fine, and you can all still hear me fine?
Yeah. I can see you and hear you fine. All good.
Fantastic. Okay. My name is Benedict. I'm an Apache Cassandra contributor, and today I'm going to talk to you about what we're doing with leaderless consensus in Cassandra, because I think we'll be the first real system using leaderless consensus. So I'm going to talk about some of the issues of leaderless consensus as it's been portrayed in literature and how we think we're going to address them, because this work is still in progress, so it remains to be seen, obviously, how successful it is. I'm going to start by talking briefly about leader-based consensus, so we can compare and talk then a little bit about existing leaderless protocols, and then talk about what we do differently. So briefly, stable leaders have some downsides that have been well established in the literature. The main and most obvious one is that there is poor latency for clients in regions other than the leaders. Obviously, there are some attempts to address this in various ways, but fundamentally, you've got to have a leader in some region, and clients that don't happen to be co-located have to contact it. And there's going to be some additional costs there. And less obvious ones, maybe less important. One of these is that the failure obviously takes out the entire controlled resource temporarily until failure is detected and a new leader is elected. And for me, the important one is that scalable transactions are very hard to deliver. And by transactions, I just mean multi-shard operations, because you fundamentally have to layer some other protocol on top. And there are some systems doing that, but it's non-trivial and not clear that the benefits of Sibley's warrant not pursuing a leaderless protocol. Has some advantages there, which we'll cover later. But obviously, Sibley's do have some significant advantages, and that's why everyone uses them. I mean, ignoring the fact that they are probably somewhat simpler. They, as implied by the prior slide, do offer optimal latency for clients in the region of the leader. And this is optimal even under failure, as long as the the leader might have to relocate to another region, but ignoring that, assuming there is a leader in the region of the clients, under maximal failure, the leader is always going to be able to exchange the minimum number of messages, the same number of messages for every single operation, F+1 messages, in order to reach some kind of decision. This, basically, any replica can take the role of the leader without penalty. These properties provide quite predictable performance, which is, I think, a significant advantage of leader-based protocols. There are some other ones we can discuss in the Q&A afterwards, maybe, but these are the ones that we're going to address that are shortcomings of leaderless protocols. So this is a quick crash course in leaderless consensus. We can discuss how we make it better. I'm sure many of the people watching are aware of how leaderless consensus works, but maybe some don't. So hopefully this slides won't be boring for everybody. We're talking here about Apache-derived consensus protocols, and they all follow a kind of a similar approach, which is that a command or transaction is coordinated by what's sometimes called a command leader. I call a coordinator, but a process that coordinates the transaction independently of all other consensus decisions. That just makes a decision about where that transaction or command will be ordered with respect to others, how it will be ordered with respect to others. This is done by an independent Paxos consensus-like setup, usually with one or two special initial rounds that the coordinator the initial coordinator has in its tool belt, and then afterwards devolves to basic Paxos consensus. And that durably decides the command's order with respect to other typically non-commutative commands, and then execution just follows whatever is decided. And so, unlike a leader-based protocol, any replica, or in some cases any process, can perform that function. And most systems, at least in the normal happy path, of a two-round voting system, they have an initial fast path decision where if a supermajority, which is usually 3/4 or so of replicas, agree unanimously on the ordering that should be applied, then a decision is reached immediately, durably, and can be recovered And if for some reason you can't reach a supermajority or they disagree about the ordering, then typically a second round trip, which is performing essentially a Paxos accept, or A1B, I think is the often referred to, phase to durably decide one of the possible orderings that might have been suggested or implied by the responses. And there are three broad categories of, I think, leaders protocols. There's the OG ePaxos, which agrees dependencies, and dependencies are the transactions or the commands that were witnessed to precede the command that's being voted upon on the voting replica, the replica that's saying what its decision is about ordering. And in the case of ePaxos, that needs to be agreed precisely. So every voting replica has to respond with exactly the same set of dependencies in order to make a decision. And so let's say we've got two transactions, an A on the left and B on the right. You can see that A arrives first on a supermajority, but B arrives second on a minority and first on another minority, and that leads to high conflict rates. There is following ePaxos, there was a protocol called Caesar developed that agrees a timestamp and a set of dependencies. So it still orders transactions eventually on the dependencies in the same way or in approximately the same way that ePaxos does. But a decision is reached if transactions arrive in ascending timestamp order. So if the most recent transaction or command witnessed by a replica is, if the command when it's witnessed has the highest timestamp that's been witnessed. And so if you've got transactions 0 and 1 rather than A and B, you can see here that you get fewer conflicts because both 0 and 1 arrive in ascending order in this example, so the exact same example as the ePaxos case. But it's not like a panacea. You still can have, as always, you can have things arrive out of order at an even like minority or any other subset of replicas, and so there's still going to be failures to reach a consensus in one round trip. And unfortunately, Caesar has some other problematic characteristics that lead to probably being undesirable to deploy in a real system. Worst case of 3 round trips, but also no actual guarantee that any of those that those 3 round trips will complete in a bounded period of time. I think it's a very unlikely scenario that you actually have this kind of live lock occur for any extended period of time, but still, even the 3 round trip property is suboptimal. And finally, one slide in this, you're going to talk about it in April. There's a tempo, which is the first, I think, leaderless protocol to do a good job at multi-shard operations, although with limited semantics. And had to, since it agrees only timestamps and no dependencies, it has the same properties with regard to conflicts as Caesar that I just mentioned, but it has much better latency characteristics. There's no potential delay to commit or execution. But it trades away the commutativity property of most leaderless protocols, so that commands have to be serialized even if they are commutative. But all of these protocols, not just tempo, have the property of being quite easy to turn into cross-shard protocols, so that they can execute transactions across multiple shards simultaneously. And they can all do this in a pretty straightforward way, which is to essentially turn the success criteria for any phase in the distributed state machine from a quorum in one shard to just being a quorum in all of the shards simultaneously for that phase. And they pretty much map directly with that. You have to remove the optimization that many of these protocols use, which is that the coordinator is a replica, or you need to proxy votes for each shard through such a coordinator. But they can all quite easily be translated into then a cross-shard protocol in this way, which is something that obviously isn't possible with leader-based protocols. And then if in the case of tempo, because it's a timestamp protocol, then it's already ordered globally. But in the case of a dependency protocol such as Janus or Janus Star, then just taking the union of all of the dependencies from all the shards is enough to correctly order your execution. Obviously, if you execute after all of the dependencies in each of the shards, then you're going to be ordered after all of the middle shards. We can discuss it maybe a little bit more carefully in the Q&A. Bring us back to this is like the opposite of the downsides of the leader-based protocol slide at the start. Leaderless protocols offer clients in any location similar latency, not identical latency, obviously, because of homogeneity in the network, but similar latency. And we can offer strict serializable transactions quite easily. Obviously, it depends on the characteristics of the underlying protocol. Apache, I think by default is only serializable, and you have to modify the semantic side to make it strict serializable. But it's reasonably straightforward to offer strict serializable isolation with the same properties as your single shard operations. And additionally, I think they have much nicer failure properties on the whole, because failure at any point of any coordinator only takes offline the transactions that would conflict with transactions that were in flight and being coordinated by that coordinator until they can be essentially have their leader election performed for those transactions. But I'm sure most of you are already aware, but those who weren't may have inferred from the slides, there are some downsides to leaderless protocols as they're described, or as I just described them. They have what I've just called in the paper for stability and under failure. And what I mean by that is that unlike a leader-based protocol that, as we discussed, can always elect a new leader under any level of failure that's tolerated by the protocol, a leaderless protocol with its fast path that requires 3/4 of nodes to be alive and healthy will, in the face of only half as many failures as the leader-based protocol, suffer a significant increase in not only the latency experienced by clients, but also the overall work being done on the system, which is, I think, highly undesirable. And additionally, that unlike leader-based protocols, contended keys reach a green more slowly. So this is almost like a leader-based protocols prioritize performance in the case of contention, and leaderless protocols prioritize it in the case of geographical distribution. But this is clearly a downside to leader-based protocols, and in combination they make performance of these protocols likely less predictable in various important scenarios. Additionally, they also have worse best case performance, because the protocol must always, in the case of a fast path, to reach a fast path decision, must contact more regions in order to reach a decision. So it's going to have to, at a minimum, travel further to reach a decision ordinarily, unless you somehow have a homogeneous network layout. So the question is, can we do better? And the answer, I hope, is yes. So the first question to answer is why these fast paths are so big, because that's what leads to us having, I think, the biggest flaw of these protocols, which is this poor stability performance under failure that you can tolerate. And the answer is you have essentially it's in the fast path that the difficulty occurs, and you can have two fast path operations crash simultaneously before their decision or their outcome, or at least two potential fast path operations crash before their outcome is recorded durably. And you need to be able to obviously recover the correct ordering of these two transactions with respect to each other. And we don't know if either of them took the fast path, because we need to be able to answer what happened with a simple quorum, because obviously this needs to be able to run under any number of tolerated failures. And to do that, we need to really see the different properties used by each protocol, but fundamentally we need this simple quorum to be able to see the two transactions ordered with respect to each other, which essentially boils down to them needing to overlap or intersect, the simple quorum needing to intersect the intersection of these two fast paths. And so, armed with this knowledge or this abstraction, can we do something to shrink the size of these fast paths? And the answer is yes. We can use the ideas of flexible Paxos, in this case actually using them it genuinely dynamically during the lifetime of a protocol. What we can do is we can exclude nodes from eligibility for the fast path. We can form what I've called a fast path electorate, which is a subset of the replicas that are permitted to participate in fast path quorums or fast path decisions. And you can see, I don't know if you've noticed that, but by taking away these two nodes, each of these fast path quorums can shrink in size by 1, and we still are able to overlap our recovery quorum in the exact same way that we could before. And we can do this right up until maximal failure, and then we're just left with essentially 2 simple quorums that are overlapping, because every fast path at this point has to contact the same nodes because every other node is down. There's no more nodes to fail, so they have to contact those in order to reach any quorum. And as a result, we can always, under any number of failures, reach a fast path decision. So we never suffer the failure stability problem that current approaches to leaderless protocols experience. This is probably more useful for the Q&A, but this is a comparison of Accord's properties with other leading protocols. Obviously, it goes down to essentially in comparison to multi-paxos, the F+1 fast path in inverted commas. Obviously, it's not quite equivalent for multi-paxos, but in that case, obviously, any failure of any of the voting replicas would lead to a need to reconfigure in order to reach decisions, or at least fast path decisions, which is anyway strictly better, obviously, than a multi-paxos world, because you always, in this case, a worst case 2 round trips during any leader failover scenario, and can scale all the way up to similar to ePaxos and other protocols, obviously, just without the coordinator is a replica optimization. So one bigger in some cases.
Hey, quick question, if you don't mind.
Yes. Yeah, absolutely. Yeah.
What's the difference between robustness and stability in this table?
So the idea here, here's a good question, and I forget that probably not necessarily read the paper, or the paper didn't make it clear. This is just me attempting to make a distinction between what the protocol overall can tolerate, so that whether or not stability is the given reconfiguration. Say if you're permitted to reconfigure to then tolerate some change. Robustness is the ability for a protocol to continue unimpeded without any change to its configuration, essentially. So all of the leaders protocols are quite robust to failure, because any given failure will not lead to the total loss of the fast path. But once you pass the f/2 threshold, the fast path's completely gone. Whereas obviously in the multi-paxos, it can't tolerate. If you're unlucky and the failure is the leader, then you have to then immediately the fast path in inverted commas is taken offline until you can reconfigure. But you can always reconfigure, if that makes sense. Did I make that clear, or shall I?
Okay, thank you. Yeah.
Okay. But we can talk about that more absolutely in the Q&A. I'm racing through these slides, partially because I fear that this stuff is mostly well known to people in this audience. So shout out if I'm going too quickly, but we'll go back over it in the Q&A as well. This approach also allows us to bias our performance. Like as we discussed, leader-based protocols in many ways have this significant advantage that they can bias performance to a given region. It's not just the downside. There are situations in which it is highly desirable to get optimal performance in certain regions where you can, with high confidence, co-locate your clients. And so with this approach, leaders protocols can bias themselves to an electorate of F+1 replicas where every member of the electorate achieves the optimal latency. And additionally, everyone in every replica in a further away region still is able to achieve 1 round trip consensus. They just have to travel further. There's no additional round trip back out to get seek votes like there would be with a leader-based approach. And that addresses the first of the approaches that we're employing to make leadless protocols viable. And the second is essentially, I've only left one slide for this because it's with a couple of modifications to it, because it's essentially something you just discussed very recently in this group. It's very similar to Paxos Revisited timestamp ordered queuing, but with a couple of tweaks. First, we use or assume a timestamp protocol. So instead of synchronizing the order to some arbitrary point in time, we synchronize it to the timestamp that is going to be used for the consensus decision. And we additionally just account for clock skew as well as network latency. And here's my little, one of my only diagrams of example of a transaction starting at T0 but traveling further and say 30 milliseconds away and traveling halfway there, or a little over halfway there, and the transaction starting at T15 and arriving before it and ordinarily invalidating it. But obviously, if instead the receiving replica waits another 20 milliseconds, which is the difference between the link latency plus some amount of clock skew, which I haven't demonstrated here, then when it processes them in timestamp order, then it will permit both to, will cast a fast path vote for both of these transactions. And if our assumptions are correct in this world, because if our skew assumptions and our latency assumptions are correct, then we're guaranteed consensus, because this is the only thing that decides whether or not we reach a fast path decision, is the order of processing of these timestamps. And importantly, if we get it wrong, nothing's broken. The worst case scenario is that we just have a second round trip to contend with. So we can actually be very aggressive with our assumptions about these skew and latencies. And indeed, we can even apply it differently for different keys. Like, for instance, it could just be not applied for keys that are not contended and only applied to keys that are contended or are experiencing contention. But if you were to utilize this this approach, a pertinent question is, which timestamp protocol would you want to use? The only two that I'm aware of have these, are the ones that I discussed. They have these suboptimal properties of the lack of commutativity in execution for tempo, and this worst case of 3 round trips and unbounded commit latency for Caesar. So this is introducing a chord, and this is where I realized I've really compressed all of the difficult content to just a couple of slides, because all I'm going to talk, there's only a couple of slides to discuss the chord, partially because I don't have any good diagrams. And then we'll be quickly into a Q&A where I'm sure there'll be lots of questions. And so assuming some familiarity with existing Paxos approaches, the idea of chord is that we agree a timestamp, much like we did with Caesar, but rather than agreeing dependencies, we derive dependencies from the responses to the timestamp agreement. And the idea is that much like with Caesar, we propose a coordinate proposes a timestamp that for the execution time for a command or a transaction. And if it's the most recent conflicting command to arrive, then a vote is cast in favor of that proposed timestamp. And if it's not, then a new transaction execution time is proposed by each replica, and each one of these timestamps is globally unique. So each replica appends its own identifier to any timestamp it allocates, and makes sure that it only allocates unique timestamps locally. So what we essentially have here is a Lamport clock, where this is how I like to think of it anyway. I don't know if it helps people to think about it, where any possible quorum leads to a valid ordering of a valid total order on the execution of the transaction. And if you have a supermajority or fast path quorum, assuming you've shrunk the size of responses voting for the original timestamp, then it is possible to durably recover that as a decision. And we'll talk about how in the next slide. And otherwise, we just need to durably persist one of the possible Lamport clock values that we could have derived from the responses that we've received. So the maximum of any simple quorum can be then persisted in an accept round, essentially a Paxos accept round, with a standard approach of a privileged initial ballot, fast Paxos style the original coordinator. So off the back of the responses for both the pre-accept and the accept round, there will be a set of dependencies is sent back to the coordinator, which assembles them in an inconsistent manner, by which I mean that each time a new coordinator takes up the role of recovering or coordinating this transaction, it might assemble a different set of dependencies. But each of the responses contains all transactions that have been witnessed by a voting replica that were proposed initially an earlier timestamp than the timestamp being proposed here. And so this encompasses the total set of transactions that could take an earlier timestamp, that could be executed before this transaction in question. And so all that then happens is that we prune that set consistently by waiting for the contents to commit, and then removing those that actually are decided to have a higher execution timestamp, and then we just wait for those that actually have a lower execution timestamp to execute before we're able to execute. If that probably very, very quick to go over that, but so we'll come back to it, I suspect. Then that brings us just finally on to the recovery mechanism, which is different to any of the other protocols that are around. And so like Epax and Caesar, we still send the dependencies that we've assembled at each one of these rounds on the coordinator to the voting replicas. But they aren't used to be recovered in a consistent manner for execution. They're used for recovery of other transactions. And the basic premise here is that we, when we're coming to recover a transaction, if we don't know the outcome of whether or not, so if we can't rule out it having reached a fastpath decision, but we can't rule in it having reached a fastpath decision, then we look at conflicting commands that would have superseded it, that would, in being agreed, have prevent it from later reaching a fastpath decision, and necessitate it having a higher timestamp agreed. And we simply say if any of these transactions didn't witness the transaction we're recovering, then it cannot have taken the fastpath. And as a result, we can propose another timestamp. Conversely, if all of these transactions have witnessed it, then it doesn't matter if it did or did not reach take a fastpath decision, because they're all going to necessarily wait for this command to commit before they execute. And as a result, we can propose the fastpath timestamp, the originally proposed timestamp, safely, because we know that all of these transactions that conflict with us are going to be ordered correctly with respect to us. And as a result, we can, we just propose that in a slow path. And there is a slight edge case here where we can have transactions that were proposed an earlier timestamp than us, but may be assigned a later timestamp than us, because we've seen them, say, in an accept round, and also haven't witnessed us. And these transactions, we can't say for sure how they'll be ordered with respect to us, but they form a strict, like a directed graph that we can always wait for those to commit safely and not affect liveness, if we happen to fall into this edge case and then retry recovery, so that we'll either see that they didn't witness us, and as a result we didn't take the fastpath, or they did witness us, and as a result, by the prior argumentation, we're fine to propose the originally proposed timestamp. And that's actually the entirety of my slides on this topic. I now wish I'd done some diagrams, as has been proposed to me before, but had that regret too late in the day to sort that out, I'm afraid. So and finally, I'd like to say thanks to a bunch of people who've helped put this work together in various ways. Many of whom I think are on the call, so hi. Yeah, I think that's everything.
All right, awesome. Thanks for the presentation. I will leave the floor open, for the discussion, I guess. We have 30 people here. I hope we find someone who is not shy to speak up.
I can start. This is very cool. I'm curious about the worst case guarantee of, I think, 3 round trips or 2 round trips.
That was Caesar. It's two round trips for a chord. Yeah, sorry, I should have made that clear. Yeah, a chord guarantees prompt commit and worst case of 2 round trips, assuming no failure or anything, obviously.
Gotcha. If you fall back to classic Paxos, doesn't Paxos have a live lock possibility? If people keep...
Yeah, I mean, but so does leader election.
Okay.
It's the exact same thing as leader election, essentially.
When does the worst case apply then, and when doesn't it?
So the worst case of 2 round trips applies in the case where the assumptions around network latency for the buffer are invalid, or you choose not to employ that optimization because it doesn't make sense, because say you're only operating in a single DC and there's no value in accounting for network heterogeneity, and there's contention. So in the case of so you have to suffer both of those things. You have to not be using optimization, or it has to fail, and you have to have another transaction race with you for agreement on that key. And in that case, you'll take 2 round trips.
And you fall back to a regular quorum rather than a fast quorum?
Yes, yeah.
Okay. What prevents 2 proposals from each getting, well, what prevents 3 proposals from each getting a portion of the electorate?
In what sense? What do you mean by getting a portion of the electorate? They can each get different votes, and if they are conflicting, and because of the this optimization to buffer correctly so they all play in sequence, then yes, then potentially none of those will take the fast path, and they'll just take a slow path decision. So okay. In that case, you take 2 round trips. Yeah.
Okay, I guess I'm just trying to understand how the fallback is guaranteed to complete with a single additional round trip.
Because you've already got there's the responses to the fast path quorum form a valid total order. They just give you basically a Lamport clock value or potentially multiple Lamport clock values, all of which are valid total orders on this transaction. You just need to agree one that's durable that anyone else can recover. And so the second round trip is just saying this one. Let's just all okay. Say just use this one and make sure, because I'm going to use this one, and once I've recorded it, now everyone else will use this one, and as a result, everyone knows what the correct ordering is.
Great. And the original coordinator is the same one who looks at those orders, chooses one, and broadcasts it?
Right, essentially, yes, yeah.
Okay.
Then the same thing would happen if a recovery coordinator were to take over. That's what they would do. They would seek essentially they would get a quorum back, which would tell them at least one Lamport clock value that would be valid to propose, because they will get the same responses that the original coordinator did from those replicas. Obviously not necessarily the actual same responses, because they might get different coordinators, replicas responding, but right, they would just do the exact same thing. Then that's their recovery process is broadcasting a timestamp that would correctly totally order the transaction.
So here is where we maybe getting into modern 2 RTTs, right? Can you have a recovery coordinator churn? They keep failing, and
yeah, but the same thing can happen with leader election, right? I mean, it's not fundamentally any different. Yeah, obviously. I mean, anyway, anytime you talk about these protocols, I think everyone agrees that we're not like breaking the FLP like result.
Okay. So it's 2 RTT is the worst case when actually things are good.
But I mean, that's true for. I think that's again, that's true for every. I mean, like, let's say like one I mean, when you talk about multi-factors or raft, they equally are able to never reach a decision. So yeah, I think it's only, I mean, in my experience when talking, well, at least on the papers, when they discuss these protocols, they're always discussing the situation where the original coordinator doesn't fail. And if they do fail, then yeah, we can discuss how many round trips recovery would take, assuming that recovery coordinator doesn't fail. But if you're talking about the possibility of recovery coordinators competing forever, then I mean, we're just at FLP really, and it's not probably that interesting, I think.
Great, that clears it up. Thank you.
Hey, sorry, I'm late to the party. Can you, yeah, I wasn't able to watch your presentation. Can you tell me about the comparison to Tempo? What in terms of approach and in terms of outcomes?
Yeah, I mean, the main difference, I suppose, is that Tempo only agrees a timestamp, and that we agree a timestamp and derived dependencies, so that we can execute. We can execute commutative operations concurrently. Another difference is that Tempo, I think, has very poor failure properties, but I don't think those are inherent to Tempo. I think you could choose totally different quorum structures to get around that. But we assume that you want to have maximal failure tolerance, and Tempo assumes that if you want to get good performance, you want to have just only one failure tolerant, one replica failure tolerance.
So what is in terms of approach taken, is there any similarity, or what is the main innovation? I'm sorry.
It's actually quite different, except that I would say, so the main similarity is that Tempo is the first, I think, protocol to perform cross-shard transactions reasonably straightforwardly or reasonably well. I mean, they only do store procedure semantics, which are obviously not very powerful, and I haven't given much thought to modifying it to do better semantics, but I'm reasonably sure it wouldn't be very hard. That's the main similarity, I would say, with Tempo. The other is obviously we're agreeing a timestamp, and in that respect, it's a timestamp leaderless consensus protocol as cross-shard transactions, so it's probably in many ways the most similar protocol. Caesar is probably in some ways closer, except that they don't support cross-shard transactions, but it could be ported to. So like a Janus star that used Caesar, it would maybe be the closest protocol to what we're using here.
And in terms, okay, so I see that in table 1, like Tempo cannot do concurrent reads, Accord does, and contention round trips 2 versus 1. Can you tell a little bit about that? Since I recently, skimmed the Tempo paper, maybe that will help me put this in context.
In what sense? So the main difference is that the contention round trips, this optimization could easily be applied to Tempo because it's a timestamp protocol. Okay. Is that we buffer, or we in a suitable deployment and suitable topology, we buffer messages on recipients on replicas for processing based on the distance traveled from the coordinator that sent the message and the known clock skew in the network. It basically is ePaxis Revisited that was discussed only a few weeks ago, with some additional tweaks, being that since we're a timestamp protocol, if you process the messages in timestamp order, then you're guaranteed to reach fastpath consensus. So this optimization could easily be applied to Tempo.
Yep. So basically, based on time of flight, you give the timestamp a little bit in advance, further into feature, so it doesn't. Okay. That was the optimization that came to my mind when I was reading it. Okay. And in terms of concurrent read.
The difference is that Tempo doesn't permit commutative, doesn't deal with commutativity because it doesn't take dependencies. So everything has to be executed on the replicas in timestamp order only, which I think is in real world likely to be actually quite a problem for the protocol. I don't think it's impossible to modify Tempo to avoid that. At least for reads, I imagine there would be a way to tag reads, for instance. So I don't know if that's necessarily an inherent restriction of Tempo, but I haven't given enough thought with respect to Tempo's protocol, to be honest. Partially also because of the failure properties of Tempo, which again could be modified, but it didn't seem advantageous to think about such a heavily revised tempo.
Yeah.
So on a high level, the timestamp gives you the ability to schedule the transaction slightly in the future, right? To avoid unnecessary contention. And the dependencies allow you to reorder the commutative transactions.
Yes, yeah, basically, yeah.
Okay. I think you touched this in your talk, right? Or like when Jess was asking the question about, like obviously the time synchronization right now becomes important, right? You said it's not important for safety, but it's important for performance,
yeah.
right?
Yes, definitely, yeah.
Like any.
I mean, in the real world, time synchronization seems to be adequately solved, I think, is the nice thing. And most data centers have, even without advanced clock synchronization, most data centers have some high quality time source, and just regular NTP. Regular NTP gets you within like a millisecond or so in most data centers, and it's only with respect to the local time source, which is high quality. So every data center that's geo-distributed is going to be maybe drifting by 1 or 2 milliseconds most at most. I think in AWS, somebody from Netflix did across their whole fleet like an assessment of time sync, and it was like micros across the whole of every single thing they were running. So in a lot of real world data centers, it's not an issue.
Yeah,
but sometimes you can have, obviously you can have situations where they aren't synchronized, and in other protocols like a Cockroach, for instance, safety is potentially violated depending on if you're relying on strict serializability. And so here you just, oh no, that one transaction took 2 round trips.
My experience with time synchronization, I mean, goes a few years back, at least a few years back, and I wasn't so happy with how the time synchronization actually works in, at least as I said, like a few years back in these data centers. I mean, not so much about the time synchronization itself, but and maybe things have improved quite substantially. So maybe I'm speaking about like something that's so ancient, but like in virtual machines, I observed that the time skew grows so fast and so so quickly that you essentially have to resynchronize the time quite often to keep it within a good window. Especially if the virtual machine is kind of busy, right, doing like other stuff.
So I guess it's a long time since I've looked into time sources and virtual machines, and I know that they have, there were definitely issues earlier on, although I think that was more than a few years back with regards to the time source that was being used in virtual machines. I can't say for sure this wouldn't be an issue in virtual machines, and in that case, probably you might want to consider not using this optimization if you're talking about like tens of milliseconds of clock speed. There's a real possibility that in some real world deployments this wouldn't be useful for sure.
Yeah, and the bigger issue for me, honestly, and when I say issue, just a bigger problem in terms of like time sync, right, is like maybe we can get time synchronization within a few milliseconds at the data center level, right? Which is nothing if you have like a cross data center latency of 50 milliseconds, right? But then like knowing this cross data center latency is also problem, right? Like right now it's 50, but where is the guarantee that next second your packet's not going to take some other longer route, and then it becomes 75, and your assumption essentially this difference between 50 and 75 is like having this extra 25 milliseconds of time uncertainty just added randomly for some packets and maybe not the others.
Sure, but like so. The thing I would say to that is that obviously you only care about this for contended keys, as I mentioned. So you don't even need to necessarily pick a real number. You could just ratchet up a number for keys when you experience contention. As a result, transactions are taking longer, and just not apply this optimization at all for other keys, because most of the time keys aren't contended, depending on the workload.
I'm sorry, I'm just trying to pick these little pieces that will create you like big performance variability potentially, right?
Potentially. But again, we're talking about like here a kind of a discontinuity where like if you have a spike in packet latency, you're talking about a potentially a significant anyway in perturbation in your performance. And these are basically going to be in your P99, P99 kind of like outlier operations anyway. And so it's just I'm not convinced this is likely to be a significant additional burden.
So I guess to finish up this point of the discussion, one more thing. If you look at the leader-based protocol, right? So you said, this extra spike in latency will have an impact on the leader-based protocol. Absolutely, it will have an impact on latency of the protocol, but it doesn't create more work for the protocol. Whereas here in all of these leaderless protocols, it does create more work. Right. So
that's true.
And this is where my concern comes in. For example, like I've been looking at this, metastable failures, right? And we found that like even small issues like garbage collections on some systems have caused this cascades and failures, right? And now we have this system that essentially can change in its processing capacity depending on these external factors like flaky network or bad time synchronization, and all of this can be like triggers for bigger failures, like in terms of the performance degraded, the throughput degraded, and
I mean, but you have to, and for this to cause a problem, you have to have a bunch of different things coincide. As you say, it's not just you have to have this occur for operations that were themselves operating on contended keys. So yeah, you're right, but I'm pretty sure I can come up with some scenarios that I haven't thought about right now that leader-based protocols would
they surely do. I'm not saying that they're like
no, I mean, I agree. There's absolutely scenarios in which you will have some additional work done. My assumption is that in most of these scenarios, the additional work will likely be modest, and obviously, anyway, clusters have to accommodate some additional work. But yeah, you're absolutely right.
The leader-based protocols, they suffer from different issues. I mean, you mentioned it yourself, right? Obviously, having a single leader, whatever happens to this leader, it crashes. That's your spike in, that's your performance degradation, right? Or the leader is slow, that's your issue. The garbage collection of the leader, whatever, to slow it down, obviously will have the same, impact. So, and I guess my big request is, can we have protocols that are not susceptible to at least some of these issues, right?
I mean, it's worth bearing in mind that the leader-based protocols are probably in some ways more insulated from this, because in a leader-based protocol, if you have flakiness in the network, your batches of transactions are going to all be delayed, and potentially you're going to have to try and figure out other ways to maybe send more commits or something. But if you have a fast path because you have enough healthy correct replicas that has more voters involved than are necessary, then at the very least, the number of links that are going to be involved in any decisions that are affected by these sorts of flakiness is going to be a lower proportion. You're going to have only those coordinated by a coordinator that's transferring messages across the link, and also there's a good chance that they will be also sending enough messages to other links that aren't affected, assuming it's not a link that's coordinated. You can have correlated degradation. Obviously, you have them sharing part of the path to a different data center or something. So obviously it depends heavily on the network topology. But it's entirely plausible to me that the system could actually be at the very least exposed to a much lower, maybe a higher risk of any of these failures having some impact, but a lower overall impact than any one failure, and maybe a slightly lower risk overall due to the higher redundancy in the fast path. Because obviously, if one of these links just takes a long time, it doesn't really matter. It's only if sufficient links take a long time there's a problem. But yeah, you're absolutely right. It's a very fair point, and I'm not sure. I fundamentally kind of inherently kind of feels like the only way to kind of accommodate that is to artificially slow everything down to accommodate for some tolerated additional maybe penalty introduced by a failing link at some point, which is maybe not even necessarily a bad idea, although I think most people would probably be reticent to do that, because I think if you're running everything as efficiently as possible, I would imagine any kind of problem like this is likely to cause some kind of negative impact. I don't know. Interesting thought. I haven't really considered how to make a protocol resilient to that personally, at least.
Yeah, I mean, we're also optimizing for best case performance, right? But what we're talking right now is worst case performance, which is a whole different thing altogether that
yeah,
we're not considering.
And this is again, like, you know, we're so incentivized to go for the best case performance, but the worst case performance is the one that crashes you. Right?
Well,
like,
I think
that's true.
I think one of the reasons that leader-based protocols are so prevalent is because of their best case performance, though, and so you have to be competitive with them in best case. But I actually think one of the reasons to prefer leaderless protocols is that they are, on the whole, better for failure in the normal kind of worst case. In most sorts of failure scenarios, I think leaderless protocols offer you greater resilience and less service interruption. And so, yeah, and I think, yeah, I will give some thoughts as to whether or not this is likely to be, whether or not there are any mitigations that can be created as well for this. It's, in the worst case, I imagine it's just, though, that in this case you would just increase the latency once detected that it was taking too long and we were hitting contention.
Yeah.
If the system were under too much load.
And obviously, you know, the worst case performance for all of these protocols is no performance, right? Like, you know, you just, you know, getting into the spiral, like, you know, leader churn in draft, or, you know, multi-paxes, or, you know, it's probably a little bit more difficult to get down to that level because, you know, in the leaderless protocol. So in that case, I guess it may be more difficult to reach this absolute, you know, bottom. The question is how easy it is to reach deep enough for it to make an impact on, you know, kind of the rest of your infrastructure potentially, right? Or
yeah, absolutely.
Yeah. So you know, if it's difficult to reach the very bottom, you know, that's great. But if it takes almost no effort to, you know, significantly degrade from the best case to, you know, this kind of intermediate case, then that may not be a desirable property for you know, production grade systems.
Right. I mean, the example that you're giving, I think, is not necessarily categorically different to the discontinuity created by a leader election. You're talking about the protocol having to detect some kind of a fault and adjust its parameters so that it no longer. So you're talking about buffering things for longer, basically. And is that fundamentally different to? Obviously, you have a brief period in which you're exchanging two messages instead of no consensus being reached in the case of, say, a leader election or failure. And I'm not convinced that's I'm certainly not convinced that's a critical concern, but yeah.
I think it's already technically best practice for Cassandra users to have some form of time synchronization NTP running. Do you have a sense of how often that's actually true versus people just YOLO their database?
I don't, because I have lamentably little contact with real users and have done despite being on the project for a long time. My guess would be probably that YOLO is a lot more common than you might like, but that's just maybe me being jaded.
What is the state of this in terms of deployment being integrated to Cassandra, etc.?
So it's currently a prototype library that has that's been published and that is being actively developed, and there is some work that hasn't been published to integrate it with Cassandra. So we have run some real Cassandra queries that touch multiple keys through its integration with the prototype, but it's very much not anything like a production quality yet. Even the prototype isn't fully complete. So it's going to be some time, several months at least, before it'll be seen in the real world in Apache Cassandra. I don't want to suggest any concrete timeline, but this year.
So are we talking Cassandra 5?
Probably, yeah, probably, yeah.
Because it took quite a significant amount of time to go from 3 to 4.
Yes, then we get into a whole other separate conversation about the dynamics within the project that caused that, but that's probably a whole other unrelated talk. The project's a lot more. There's a lot more activity and and velocity now. So we're actually expecting a 4.1 in a few months and 5. So I know I anticipate it being ready probably quite a while before 5 is released, unless we maybe accelerate 5 because this is so cool. I don't know, we'll see.
So how does it exactly? How do you envision this actually integrating into Cassandra? Like you mentioned, right now it's a standalone like prototype library. I mean, Cassandra's data model, is anything but transactions. So I'm just kind of curious how it will.
Actually, bear in mind when we talk about transactions here, we're not talking about interactive transactions. I'm sure you realize. Okay. Because that's a whole other kettle of fish and quite complex. There'll be some probably evolving support for that.
Are we talking like compare and set operations that use Paxos right now? That kind of stuff at first, or
yeah, the initial probably API will be I imagine a cleaned up a version of the atomic batch, what they call LW, lightweight transactions, as they call them, but supporting multiple keys, basically. Yeah. So you'll be able to do, and maybe also rolling in the ability to do select statements and things like that simultaneously as well, so you can actually get some data back atomically. That's as yet undecided. But the prototype is going to remain the actual implementation. So the implementation is going to remain kind of separate as a kind of a standalone protocol that is going to be then plumbed into Cassandra. So you'll be able to, if you want to, play with the protocol in other, at least Java-like systems once it's finished. Did anyone else have any questions? I assume we're running out of time, but I don't know, we covered a lot of.
Were there more conversations on interactive transaction model or the sort of query language or being able to do more complex evaluation of things in the non-interactive transaction model?
No, we haven't thought about that in large part because it's such a large amount of work to get one-shot transactions delivered. So I think it's very likely that more complex, at least somewhat interactive transactions will be delivered in follow-up to this work, but I don't know when or in what shape. It is going to depend on the different companies that are resourcing the development of Cassandra. So it's too early to talk about, really. I wouldn't know how to answer.
Yeah. Also, like in the context of Cassandra, just something that came up to my mind. Obviously, you've been working on this for quite some time, I suppose. The recent Pat Hallen's paper, like from last month, that talks about the transactions, right? Like, this hypothetical thought experiment of a database, and I'm thinking that something like this can be layered over like the Cassandra storage and Cassandra database itself.
Potentially, I don't think I've read that paper. I'll have to.
It does offer interactive transactions, and it relies on sharded storage, and each shard is just like a quorum kind of based system where like you don't have a Paxos, you don't have like a state machine in each shard, just pretty much kind of like running Cassandra, right? But there's like a bunch of stuff layered on top to build a transactional system. He describes quite a lot of stuff on top, so I'm okay. Any other questions, comments, feedback?
Oh, thank you for the great presentation, which I missed, but thank you for the question and answers section.
My pleasure, thanks.
All right, yeah, thanks a lot. And the reading group will continue next week with, actually we're coming back to paper 84, the paper that we skipped from the previous session from the previous semester.